have been discussing about problems concerning entropy transport across a control volume, and let me work out a few more problems to help you understand the concept. So, the next problem is problem number 7.7. So, a counterflowing heat exchanger. Counterflowing heat exchanger means that you have two streams, they are flowing in opposite directions and the heat is exchanged between the hot stream and the cold stream without any external heat transfer taking place. So, it has one line with 2 kg per second air at 125 kilopascal and 1000 Kelvin entering, and the air is leaving at 100 kilopascal and 400 Kelvin. Okay. The other line has 0.5 kg per second water coming in at 200 kPa 20 degree centigrade and leaving at 200 kilopascal. What is the exit temperature of the water and the total rate of entropy generation? So, let me go to the board and try to draw a schematic of this problem, which this method we have followed for all the problems that we have discussed so far. So, you have air, one line is air, and the other line is water. M dot air is 2 kg per second. The state points, this is 1, this is 2, this is 3 and this is 4. So, this is 125 kilopascal, 1000 Kelvin, this is state 1. This is 100 kilopascal. I am just writing the problem data, I have not actually started solving the problem. This is 200 kPa 20 degree centigrade and you have m dot water is equal to 0.5 kg per second. State 4, it is 200 kilopascal and there is a temperature which is not known. So, T4 there is a question mark. We can, if we can find out T4, all the state points will be identified and then we can do a second law analysis to calculate the entropy generated in the process. So, see some very interesting thing, I mean there are many practical things that come out of problem solving, that is why problem solving is so interesting. So, look at the air line, here you have 125 kilopascal and here you have 100 kilopascal, if I have not made a mistake that is what it is given. So, there is a pressure drop as the air is flowing from 1 to 2. However, there is no pressure drop as water is flowing from 3 to 4. This I would comment as an idealization rather than reality, because in practice to sustain a fluid flow there will be pressure drop to overcome viscous resistances. So, that is a practical fluid dynamics issue. Solving a thermodynamics problem does not interfere with that, but it is important also to understand that while the data given for this line is quite practical, the pressure, constant pressure assumption of this line may be a bit questionable. Okay. Now, we will find out, we will try to identify what is state 4. So, we will make a control volume analysis. So, for this control volume, if you write first law, Q dot plus summation of m dot I H I, in inlet is 1 and 3. So, m dot air H 1 plus m dot water H 3 is equal to m dot 2 H 2 plus m dot 4 H 4 plus W dot, sorry, m dot 2 we can write is same as m dot A and m dot 4 is same as m dot W. So, we can replace these. Because this is heat exchanger, there is no external heat transfer across this control volume, we neglect it, it is a primarily the exchange of heat between these two streams. The purpose of heat exchanger is not to do any work. So, the work term is 0 and hence you are left with, so you know state H1 you know, because state 1 is known 125 kPa 1000 Kelvin and this is 100 kPa 400 Kelvin. Now, although there is a pressure drop, but in terms of enthalpy, if you assume here as an ideal gas, this pressure drop does not matter, because enthalpy of an ideal gas is a function of temperature only and not pressure. So, you can write for example, what is our unknown? Unknown is H4, H4 is m dot A into H1 minus H2 plus m dot W H3. So, this is integral of Cp dt from 2 to 1. So, m dot A by m dot W, if you divide both the sides by m dot W, that will be the case. Okay. So, this will be integral of Cp dt. The range of temperature is from 1000, from 400 to 1000, it is quite large range. So, it is better not to rely on constant Cp, but calculate or get H1 minus H2 from air table, properties of air table. H3 at state 3 you know, water at 200 kilopascal and 20 degrees centigrade. So, H3 will be roughly HF at 20 degrees centigrade. So, from here you will get what is H4. So, H4 if you calculate it, it will be 2663.62 kilojoule per kg. If you look at the table, you will find that this is less than or this is between HF and Hg at 200 kilopascal. So, if it is between HF and Hg at 200 kilopascal, that means it is in the two phase region. So, how do you calculate the quality at state 4? So, H4 is equal to 1 minus X4 into HF4 plus X4 into Hg4. So, from here HF and Hg are corresponding to 200 kilopascal water HF and Hg that you get from table. So, if you substitute that you will get what is x4. So, x4 will be 0.9805. For all the problems I am trying to give you some intermediate numerical values as much as possible, because you can practice yourself and gain confidence if you see your answers are matching with these numbers at least closely. So, when you have this x4, invariably for entropy generation you need the property, the entropy at state 4. So, let us calculate entropy at state 4. 1 minus x4 into SF4 plus x4 into SG4. So, entropy at state 4 is 7.01786 kilojoule per kg Kelvin. Okay. So, then if you make a second law analysis, the change in entropy, which is m dot water into S4 minus S3 plus m dot air into S2 minus S1 is equal to q dot by T0 plus rate of entropy generation. If you take this T0, this includes both effect of internal and external irreversibility. There is no heat transfer across the control surface. S2 minus S1 so, as I told that it is important to recognize that over this large range of temperature Cp and Cv will be strong functions of temperature. So, it is better to say Cp integral Cp dt by T, this is a function of temperature 1 to 2, this part is fine, R ln P2 by P1 is. So, this you can get from air table, the data of this is tabulated in properties of air table. So, S2 minus S1 you get in this way, S4 and S3 from steam table, from water property table. So, if you substitute that here, the entropy generation will be 1.54 kilowatt per Kelvin. Okay. So, let us move into the next problem, problem 7.8. An insulated tank is to be charged with R134A, which is a refrigerant, from a line flowing the refrigerant at 3 megapascal. The tank is initially evacuated and the valve is closed when the pressure inside the tank reaches 3 megapascal. The line is supplied by an insulated compressor that takes in R134A at 5 degree centigrade with a quality of 96.5% and compresses it to 3 megapascal in a reversible process. Calculate the total work input to the compressor to charge the tank. So, let me draw a schematic of this problem. So, there is a compressor which compresses R134A and charges that R134A, there is a valve in the pipeline. So, if the valve is closed, this R134A is not coming, but if it is open, then it is filling up a tank. The tank is insulated. So, state 1, so the fluid is R134A, state 1 is 5 degree centigrade and X equal to the quality is 96.5%, that completely specifies the state. Okay. So, at state 2 the pressure is 3 megapascal and then the compressor is also insulated, this is also told. So, I am just symbolically putting it. The tank initially is evacuated and this supply line is used to charge the tank, and the charging process is stopped when, that is the valve is closed when the pressure inside also becomes 3 MPa, because that is the maximum pressure which you can develop within the tank, okay, and then you stop it. The entire process is reversible. Okay. So, if the entire process is reversible, calculate the total work input to the compressor to charge the tank. So, this is the compressor and this is the tank. Let us take a control volume around the compressor. So, the control volume compressor. So, the compressor is adiabatic and also process is reversible. So, that means it is isentropic, reversible plus adiabatic. So, because it is isentropic, what we can say is that S2 is equal to S1. Since S2 is equal to S1 and P2 is equal to 3 megapascal, using this combination we can identify what is state 2 from the R134A table. S1 is from table because you know this 5 degree centigrade and quality, you know by this time how to calculate this, I am not wasting time for that. So, when you have state 2, then the question that is asked is what is the work input to the compressor. This information does not tell us what is the total mass that has flown in across the compressor. So, per unit mass flow we can calculate the work from this data. So, per unit mass, if we write the first law for the steady states, right, neglecting changes in kinetic potential energy and all this. So, there is no heat transfer across the compressor. So, W is H1 minus H2. So, state 2 will tell you what is H2. So, this will be minus 41.6 kilojoule per kg. The question that is asked is what is the total work input and not just per kg. So, you have to find out how much kg of R134A has flown across the compressor and come to the tank. So, for that the control volume will be the tank for that analysis. So, control volume tank. So, for the tank it is a uniform state uniform flow process. So, Q plus Mi Hi is equal to Me He. I am just writing symbolically, then I will substitute values. So, we use a different symbol, let us say W tank. So, there is no work done for the tank, it is rigid. So, the work is 0, there is no heat transfer, there is no exit, and M1 is 0, and from mass balance M2 is equal to Mi, right. So, you can find out. So, from here you can see that you will get U2 is equal to H1 Hi, Hi is H2. So, these two, so let us not confuse symbols. So, I will use different symbol for this 2 is final. So, this M, let us call it M2 tank, M2T, this is U2T, right. This is M1T, this is different from states 1 and 2, right, 1 and 2 are these. So, M2T is equal to Mi, which means U2T is equal to Hi, which is, so U2T you can get from here because you know what is H2 already. How do you identify state 2? You also know that P2 tank is 3 MPa, this is given, and U2 tank is whatever you get from this step. So, from pressure and internal energy, two independent properties, you can identify the state. It is quite tricky to find it out from the table, but you know you can in principle find it out. So, this will give you state 2t. Once you know state 2t, you know what is specific volume at state 2t, and what is M2t is the volume of the tank by the specific volume. So, the volume of the tank is 2 meter cube. So, this is the mass that is coming in, and so the total work done for the compressor is this total mass that has come to the tank times the specific work, which is this one. So, that will be minus 12,295 kilojoule. This minus indicates that work is input to the compressor. We will work out one more problem. Air from a line at 12 MPa 15 degrees centigrade flows into a rigid tank that initially contains air at ambient condition, which is 100 kPa 15 degrees centigrade. The process occurs rapidly and is essentially adiabatic. The valve is closed when the pressure inside reaches some value P2. So, up to 1 and 2 the process is adiabatic, then the tank cools to room temperature, at which time the pressure inside is 5 MPa. So, what is the pressure P2 and what is the net entropy change? So, let us make a schematic. So, this is the tank, there is a supply line with state I. So, the tank V is 500 liter, state I is 12 MPa 15 degree centigrade, this is all air. State 1 100 kPa 15 degree centigrade, state 2 you do not know P2, but what you know is Q12 equal to 0. State 3 at state after reaching state 2 the valve is closed. So, that means mass inside tank at state 2 and state 3 are the same, and T3 is equal to 15 degree centigrade, which is essentially equal to T1 and Ti. Okay. So, T3 is 15 degree centigrade, which is T1 equal to Ti. This is what is given. So, then what else I mean, if it is given air, so you can treat this as an ideal gas. So, straight away you can write M1 is P1V by RT1. So, this is 0.604 kg, this is R of air, M3 is equal to M2 is equal to P3V. So, P3 is given, right, P3 is 5 MPa. So, I have forgotten to write it here, P3 is 5 MPa, P3V by RT3. This is 30.225 kg. So, the mass that has come in Mi, that is M2 minus M1, this is 29.621 kg. For the process 1 to 2, heat transfer is 0. So, if you apply the USUF energy equation, so Q12 plus MIHI is equal to M2U2 minus M1U1 plus MEHE plus W, W is 0 and there is no ME. Yes, there is no dot, right. So, then M2 you know, U1 from state 1 you know, U1 from state 2 you do not know what is U2, right, this is what you do not know. HI you know and MI is already known, this is M2 minus M1. So, this will give you what is U2, Q is 0. So, U2 you will get, so if you take constant CV, this is as good as CV into T2. So, this will tell you what is T2. If you do not take constant CV from air table with U2 as internal energy, you can find out what is T2. So, T2 is 401.2 Kelvin and P2V, which is VE tank, is equal to RT2, which will tell you what is P2. This is one part of the question and this is 6.96 megapascal. Yes, yes, P2V is equal to M2RT2, yes, right. So, P2V is equal to M2RT2, from here you will get what is P2. So, this is one part of the question. Then the next part was what is the total entropy generation. So, now you have to consider the process from 1 to 3. So, Q12 plus Q23 is total Q123 is equal to, this is Q13 plus MIHI. Now, it is M3U3 minus M1U1 plus MEHE, this is 0, and the work is also 0. So, here you know everything except you do not know what is Q13, you also know what is U3. How do you know what is U3? You know P3 and T3. So, you know what is U3. So, from here you know the unknown that you can figure out is what is Q13. So, Q13 is minus 2450 kilojoule. Okay. So, this is the first law analysis. We require to calculate what is the entropy generation. So, for the second law, Q, so change in entropy is MESE minus MISI plus M2S2 minus M1S1, right. This is the total change in entropy is equal to Q13 by T0 plus entropy generation, right. So, all these values you can substitute. SE is 0. So, this is 2 is, this is actually 3 not 2, 1 2 3. This is the change, final minus initial. The change in entropy, so you look at the entropy transport equation, this is the final minus initial. So, I have derived it using the Reynolds transport theorem, you can verify it. So, you know what are these ones and this one. Change in entropy you can calculate by from the air table, and this heat transfer is known. T0 is what? T0 is 15 degree centigrade, right. So, 273.15 plus 15 Kelvin. Okay. The entropy part, see, a simple trick you can play is that Mi is M3 minus M1, then it is split into two parts. So, this is split into M3 into S3 minus Si plus M1 into Si minus S1, right. So, now you can use the difference in entropy formula, integral Cp dt by T minus R ln P final by P initial. Here 3 and I, see, this is 15 degree centigrade, 3 is also 15 degree centigrade. So, the temperature dependence part of the entropy here is 0, it is only the pressure dependence, and I and 1 also the temperature is same. So, it is only the pressure dependence. So, these entropies are changing only due to pressure, not due to temperature. Substituting the values, so the entropy change here will be simply minus R ln final pressure by initial pressure. So, this will give you entropy generation is equal to 15.265 kilojoule per Kelvin. Okay. So, let us stop here for the time being. We will continue with more problem solving in the next lecture. Thank you.